Kia ora and welcome to another online tutorial. Today we're going to be talking about rotational inertia. Okay, so rotational inertia is a measure of an object's resistance to changing its rotational motion. So how hard it is to get rotating. Okay, so it's given by the equation our rotational inertia I equals the sum of mass distribution times r squared, where m equals mass in kilograms, r is our radius in meters, okay, and our unit is kilograms times meter squared. So we get kilogram meter squared, okay? But our mass distribution is dependent on the shape of an object. Okay, with a key note here being that not all inertias are calculated the same. Okay, because as we discussed, the distribution of that mass is key. Okay, so we're going to talk through two examples here with a solid sphere and a hollow sphere. So if I draw two circles real quick. Okay, and I have my, and I'm just going to color this in a little bit to differentiate my solid sphere. Oops, a daisy. And I have my solid sphere. And my hollow sphere. The base of the equation, mass times the radius of the spheres, are the same. We're going to assume that these two spheres have a similar radius or the same radius and a similar mass, even though the hollow sphere would have that mass distributed around the outside. Okay. The equation for our solid sphere would be I equals 2 over 5 mass radius squared. Okay. Whereas that for our hollow sphere would be I equals 2 over 3 mass radius squared. Okay. Meaning that if our masses and radiuses are similar or the same, okay, we would have a greater inertia on the object which has a less central mass distribution. Okay, so our main takeaway, okay, mass distribution affects inertia. Okay, how so? More central distribution equals less inertia. Less central or more spread out equals greater inertia. So, rotational inertia, okay, it's calculated as the mass distribution times the mass times the radius squared. We use our standard index units and we get the unit for inertia as kilograms meters squared. We know that our calculation is dependent on the distribution of mass. We used our example of a solid sphere and a hollow sphere to show an example of a difference. 2/5 times the mass is smaller, or is going to be smaller than 2/3 times the mass and radius squared. Therefore, our less central mass distribution has a greater inertia, and our more central mass distribution has less inertia. Okay, the same goes for pipes versus solid cylinders, assuming mass is the same. You might notice, if you've ever worked on an engine before, that flywheels tend to have a larger distribution of mass around the outer perimeter of the arc, okay, for this very reason, as it has a greater inertia. And as we'll talk about in a future video, the harder something is to get rolling, or spinning, or rotating, the harder it is to stop, because a greater inertia is going to equal a greater rotational momentum or angular momentum. Cool. Hopefully this has been helpful, team. Hopefully you can use this to get out there and get into some physics. All the best.